Good evening, all. A warm welcome to 207th episode of Creactive Weekend Talk. Creactive is a platform that brings together curiosity minds with a common goal of learning behind textbook. Through our weekend talks series, we invite experts from diverse fields to share their knowledge, experience, and insight, inspiring us to think creatively and broadening our understanding of the world. Our creative is knowledge square. Motto is knowledge square. Sharing knowledge increases our knowledge. We believe that learning becomes more meaningful when knowledge is shared. Thank you for all joining us today. And it is now my privilege to welcome Dr. H.S. Sudhir sir for today's session. Today's topic is on exploring landscapes and riverscape through Earth observation satellite. In this session, Dr. Sudhir Sir will introduce us to fascinating world of satellite, remote sensing and demonstrating how Earth observation satellites helps us understanding landscapes and riverscapes through real world application, images and videos. We are honored to have him with us today and looking forward to an insightful and inspiring session. Before that, I call uh, Harshini. Harshini? Okay. So some problem, I think, sir. Harshini, um, Harshini, okay. Sir, over to you, sir.
Sure. All right. Thank you so much. Welcome all. I'm really glad to be here and happy to uh, share some of the work that I've been trying to do and sort of give an overview of what has been happening on remote sensing at large. Yeah, I hope my screen is visible, right? Right. Okay. So what we'll be doing is I'll possibly take you through some bit of overview on remote sensing, what has happened, particularly with Earth observation satellites, and also give some high-level examples, or at least some of the examples that we have been working through, and sharing some of the works that we have done as well, so that you get a glimpse of how things are, emerging and where it stands. So, at large, right, I think Earth observation studies in India has been carried out for about no, close to about 5 decades itself now, with the beginning of the Indian space program itself. As in, the moment when we started launching satellites and particularly for Earth observation, we are having getting data from them, and uh, perhaps from early 80s and all, we have had quite a bit of data and all of it. And since then, remote sensing uh, or with the availability of Earth observation data, there has been significant work that has taken shape and is going uh, forward as well. Now, what has come to now is that almost every state has their own geoportal, and there are a bunch of GIS related services that they are offering. And what was earlier thought to be only like the academia and government institutions has now moved to the private players. I'm sure if you have watched the news yesterday, India also has private launch that happened. So it's no longer sort of restricted to the academia and only the sort of government institutions that would be looking at Earth observation data and analysis and applications. I can maybe perhaps at the end I can tell you more about how private players are also aggressively taking this forward in all of it. And what has, I think, key takeaway also is that what has really happened over the last couple of years, in fact, is that one availability of, you know, these AI, ML, machine learning methods that are there and largely on cloud-based systems has really revolutionized the way we have been handling satellite data in the sense that no longer we are strictly downloading all the data and working with it, but now everything happens on the cloud. So from accessing data to processing it and getting analysis done and taking outputs from that, everything is happening on the cloud itself, and that has kind of really revolutionized things there. I'll share possibly some of the examples that has happened on in that regard. But while we are talking about all of this, some of the challenges also remains is that when such data is all available, uh, what becomes very critical is what is called as training data. So training data is very useful when it comes to making Earth observation satellite data and looking at it. So that's a very crucial thing that one really needs to look at and work with it. So if you look at the Indian geospatial landscape, right, at large, like I was telling now, there are a bunch of government organizations that are looking at things across. And then you also have a bunch of geospatial portals that the government itself is kind of setting up and put out a lot of things that is trying to make data accessible to the citizens and public at large. On the other side, I think something that we need to really keep note of are the policies that uh, has been really progressive, I must say, because uh, from about 2.5 decades ago, when I started like working with satellite view data and remote sensing, to today, a lot of things has changed for good in the sense that the coming of national data sharing and accessibility policy or the national geospatial policy or the space remote sensing policy that has come out and a bunch of things, right? I think has really shaped or made a lot of data more accessible in a way that is consumable to users as well. And it is the same policy that is also now allowing private players to also participate than restricting only institutions and government players to be there. Aside, we also have a bunch of private sector and CSOs who are also kind of working through it, and there are a whole gamut of things. I'm sure most of you would have used something like Google Maps if you have to navigate from point A to point B and so on. So you would have seen how to kind of go about it and work through it. Similarly, you have a bunch of them from OpenStreetMap to other private players as well. MapMyIndia is a very key player in India, and of course, you have SatShore and others who are also uh, kind of making good progress in the Indian landscape. Now, as we speak, something that we have to really recognize and acknowledge is that as we speak, there are hundreds of satellites that are simply capturing data. It's like taking a photograph from the top, and there's so much of data that is simply being collected. So the thing is that all of these satellites are literally orbiting around the Earth and taking photographs or what we call as satellite image uh, data there. So that is being captured as we speak, and that's like it's unimaginable amount of data that is being collected and like transmitted back, and processing it is another key challenge there. So if you see this that's really enormous amount of data. I can't emphasize more on that. And as I say, uh, one of the most popular programs that has been uh, very popular and also very effective as well is the National Aeronautical Space Administration of the United States, NASA's what is called as the Landsat program. That has been almost for 50 plus years now, and we have had data from the Landsat 1 till 9 now, and bunch of like if you see across the globe, you have it's got fairly very good coverage and it's still going good and one of the most popular programs of access and of accessing satellite data there. Beyond Landsat, you have MODIS that is also giving you daily composites, and then we have terrain data that is coming up, something that can be accessed uh, by even atmosphere, in fact. And that's not limiting us just to look at land in that sense. And then beyond NASA, you also have European Space Agency's Sentinel data that is available. And some of these are also very easily accessible and uh, has a very good spatial resolution as well, like at 10 meters or so. I'll come to that as in when I'm speaking some of it, I think I'll kind of try to demystify some of those uh, in the sense of the technicalities of when I say resolution and all. So we'll get into that. So with that, I think what I will do is I'll just give you a glimpse of very high level view of what is there. But I think we'll take a step back to really look at what is sort of remote sensing. Now, uh, we'll quickly look at what is the science, some of the satellites and sensors, some image interpretation and applications. Now, remote sensing is nothing but uh, like what you're doing, right? As in, I'm sure all of you are watching the screen or listening to me. Uh, so essentially, the act of watching without physically, being in contact and getting sense of that such information uh, is something called as remote sensing. So basically, the way we see and process information is essentially remote sensing. So the good part or the best part is that in the course of evolution, our eyes and our brain, and coupled with our cognitive abilities, has built in or evolved into a very fantastic uh, model and system there, which can process information as we speak. In the sense, it's not only able to view and absorb information, like you must be reading this text that is there, but the way our cognitive abilities have evolved is also that we are able to listen and then process that information. So what you see and perceive information is nothing but remote sensing in a very simple sense. So what we are trying to do is essentially mimic the whole same thing. Instead of us being able to watch, you're putting in cameras which have specific resolutions and some day variations there, and that you're trying to put it on the satellite that could capture the information of the Earth and of areas that we would really want. And based on that, we are trying to look at what is happening and understanding what is going on. Now, how it works is that we try to again play with what is what happens with electromagnetic radiation. Basically, we really look at active source of light, which is the sun, and then the reflectance that comes in. So what satellites do is essentially capture the reflectance in different energy bands. So I'm sure we'd have all studied some of these in high school physics, some of what is called as the electromagnetic spectrum and all of it. So we would know like what is the wavelength of different bands. So again, our eyes are programmed to view everything within the visible region that you see there, from like red to uh, violet there. So the entire if they are that is what we see is there. Our eyes is kind of programmed or evolved into that, watching everything that we can see there. But when it comes to our human-made cameras and sensors, what we do is that we have built sensors or cameras that will capture reflectance that is coming back from the surface of the Earth in specific energy bands. So that at specific wavelengths, right, when it is coming back, it's able to distinguish across those land cover features. So if you see the graph there, in some different bands, which could be near infrared or mid infrared, or even blue and green bands. So different land cover features like water, soil, or vegetation have different response to the incident radiation and hence different reflectance. So when such reflectance comes back at different wavelengths, they are captured separately. And that is something that is kind of really captured and tracked, and that is captured, and that's what makes it as the satellite data. Now, what happens is that uh, again, we are wired to watch things in the visible band. But what happens when in the satellite data is that it also comes like in red, green, near infrared, and so on, short wave and different energy bands. So what we do is that we also use that to create what is called as a false color composite. So what you see on the left is what is kind of in the visible branch of the true color image, but on the right hand side is what is called as a false color composite. I think I'll give a better example of that in some time. So what happens also I think is how we really look at when data comes in, there are different challenges to it. It could be cloud cover and bunch of things like that. So in fact cloud cover is one of the key causes of concern for most of us working with optical remote sensing, because like typically like now in the monsoons, right, most of the data that is captured is useless. Like unless now in the previous era, right? So what used to happen now is that like because of such cloud cover, we were not able to really look at what is happening behind. But thankfully, now there are different models, so which are able to kind of clean this whole thing. So you're able to kind of clean the whole set of things and at least get some key elements out of it. So it's not completely useless, but still it poses kind of challenges to kind of look at what's happening. So things have really moved, as in, of course, cloud cover does pose challenges, but no longer it is sort of a very critical thing. In fact, something that has also helped beyond looking at some of these challenges with cloud cover is also because is the available of uh, sh- uh, radar imaging, which is like something like that Sentinel also gives us, or microwave remote sensing, which is like not optical. So I'll talk about it a little later as well. One of the other things that we may have to keep in mind when we're looking at satellite remote sensing is the aspect of resolutions, because something like how some of you may know of, like if you're using your mobile phones, I'm sure you would have come across how many megapixel your camera is and things like that. No, that is something that is specifically related to how much of bit or what is the uh, grayscale value for RGB values that your image phone is able to support for any image. Now, I'm sure you would have known what happens when stored satellite information in a pixel is that it can be either 8 bit, 8 bit is 2 power 8, which essentially means it could be 2 to the power of 8 or 20 to 255 grayscale values. If it is 10 bit, it is 2 power 10, which is 1024. So it can have either a grayscale value of 0 to 1023 values. So depending on that, right? So if it is a 10-bit data, R can have 1024 values, G can have 1024 values, and then B can have 1024 values. So if you multiply 1024, 1024, and 1024, the cube of it will be close to a million pixels or million grayscales. So your 1 MP is essentially coming from that, as in that logic. So essentially, while that is the logic for that happens on your mobile phone, here we can't really handle such large data sets. Now, I was talking about Landsat, right? Landsat typically has a spatial resolution of 30 meters. Now, when I say spatial resolution, it essentially means the pixel, which is that rectangular patch of that least unit that we have in an image. That image, in the smallest unit there, which is a pixel, can have will is basically the edges corresponds to about 30 meters by 30 meters. Now that's the best lens that can get you, but still that is a lot of information. Now one image of Landsat would be covering about 180 kilometers by 180 kilometers with about roughly close to 6,000 by 6,000 columns and 6,000 rows. So it's like an image of 6,000 by 6,000 pixels, and that would correspond to close to 180 square kilometers. So that's a quite a bit of area. Effectively, it could cover like one of the uh, districts and or even blocks, some of the talukas and all of it. It's a fairly large amount of area in that sense. So each satellite, uh, each such one image, right, would come in a compressed of about like with 7 8 bands would come to about 400 MB just because it is about 30-meter resolution. Now, that is with respect to the spatial resolution. When it says temporal resolution, it is how many times, what is the repeativity of the satellite coming back to capture the same parcel of the land or face of the Earth. So some satellites now, earlier used to be like 28 days, then about 14, 15 days, like it would be like doing twice a month. But then now we also have something that is coming up every 5, 6 days or even 2, 3 days. Some of the high resolution satellites, uh, like some of them that comes up at 61 centimeter and all, also have a very good temporal resolution of about 2 days and all. And then the spectral resolution is also with respect to your uh, what bands one can have, and the radiometric resolution corresponds to kind of what bit length you can have. So different type of resolutions are useful for different use cases. So some are good for land cover mapping in the larger landscape. Some are good for water bodies. Some are good for vegetation. Some are good for different landscapes there. But most often, some of these also pose different challenges, particularly if your area cover has something like cloud or snow, ice, and so on. So those things also really pose different challenges there. So this is a snapshot of how Landsat has captured uh, satellite data over the years and across the globe. So if you see something smart that they have done very smartly is they haven't simply captured all the data across, but mostly focused on land. So if you see only where places in some islands, you will see it has captured, but otherwise it's mostly across all the land parcels that you would see there. So yeah, so this is a very popular program, and all of the Landsat data is very freely available and in a friendly, easily accessible way, and things have been going great with that. So yeah, it kind of continues to provide or be one of the leading suppliers of satellite remote sensing data there. Something that we would like to kind of take you through, like some of that I kind of explained earlier, was on looking at what happens uh, when satellite is data captures uh, reflectance in different wavelengths. So kind of briefly mentioned that while talking about this, some of the definitions and the basics of that a little while ago. So what we'll do is I'll kind of quickly run this video here. I hope it. And I hope that give you a sense of, how if we start playing around with different bands of the satellite uh, remote sensing data, we could kind of, get different set of things from that, right? Um, yeah, move on. So what also has happened is that because satellite remote sensing data has been being gathered for like I said, over close to 50 plus years now. Uh, Something that has happened is that now we have over 50 petabytes of Earth observation data from imagery, weather, and bunch of things. So that's the good news. And a more even better good news is that something like that Google has come up also is we have some one can use Google's computation infrastructure and sort of play around with it to kind of use Google's computation and also data that is available on Landsat or European Space Agency Sentinel and bunch of other satellite data providers and use them and kind of work with it online. Now, so Google has come up what is called as Google Earth Engine, and that's something really amazing part that has happened is because it is kind of allows you us to kind of really look at different set of things over time. So it could be even looking at cloud cover to cloud making cloud free image, and or even creating something like a blue marble. A quick question to some of you or over here. Do you think such a situation arises or is possible that you see on the screen? In the sense, will there be any day like this? So I'll give you a hint. In this, what is called as this image, it is called as popularly called as blue marble. What you see there is that there are no cloud-based cloud images with any clouds there. So all of these are cloud-free images. So do you think there is any like will there be any day that is possible on any face of the earth that there could be cloud free? Well, in reality, that is not possible. So, what has happened here is that very smartly, over a year, data from over a year has been first captured, and then data which are only cloud free has been filtered out. And then, based on such a filter, this image is kind of mosaic so that you get only cloud-free image of the Earth. So it's basically this is what something that Google Maps or most other popular Bing Maps or all of satellite would kind of use this because this is something not really physically or humanly possible in the real sense that there cannot be a cloud-free place anywhere at any given point of time on Earth. So this is an artifact of how one can also make use of available satellite data and kind of play with it. And to take you through some things that what is also has been made possible thanks to again Google Earth Engine's capabilities there. Uh, these are some of the time-lapse images that you see. So what it allows is to kind of now to look at how seasonal changes happen and things like that. Uh, Yeah, sorry. Shivsagar, thanks for the response. I just noticed. Yeah, so things like this, right? So using time lapse, we can really look at, or what really also is possible is if you look at this river, right? How uh, the river course changes over time, and also on top left, you can see how land cover is changing with the rise and expansion of cities and changing and increase in farming landscapes as well. So some of these things are really possible from satellite data, kind of look at how landscape has really changed over time. And these are fun to kind of also explore. And if you're any geography enthusiast, it's really nice and awesome to kind of simply go over and keep playing around some of these. This is one of the other things to look at is how cities expand, something that we've been also looking at of of urban growth in particular and sprawl as well across how cities are expanding and how things are changing. So some of these are also like you could look at or the deforestation in Amazon. So these are some of the examples. I have placed a link at the bottom of this screen here. It's earthengine.google.com/timelapse. Maybe some of you, if you're interested, I would encourage you to kind of go there and uh, explore for yourself as to, or go to any geography of your interest to kind of really look at and kind of create a time lapse and see. Some of these are really fascinating and kind of gives you a sense of, what has happened, how things have changed, and things to look at. Now, while these are all very sort of, visually intuitive and all, what really happens is that I think for some of us, we kind of really get into looking at data and try to understand uh, what really is going on. And if you look at, Indian urbanization itself and some of the cities that we try to kind of uh, explore, looking at it. Mapping cities and over time and all of that has been possible because of satellite remote sensing data. In fact, back in the day when this kind of a data was we had processed, uh, my team had to really spend a lot of time working through it, seeing through different images and running the processes and all of it. Uh, Now, like I said earlier, the last couple of years has been really fascinating because uh, to kind of come up with something like this, we don't need to really spend months together processing tons of data and all of that. But something that has really made possible is the availability of cloud-based computation systems. So it's not just Google Earth Engine. So you also have Earth on AWS that also allows you to kind of do this. Uh, We also have Sepal, you have OpenEO, and then Open Data Cube, a bunch of them. Uh, so in the sense that cloud-based geospatial data accessing and processing it has really moved things or moved much forward the way we are really looking at data. Uh, so something that this I don't know why I have this red line across the screen, but yeah. So beyond the cities and urban challenges, right? I think some of us are also interested to look at, the larger landscapes at large. So I'm sure some of us would know this, and uh, this is land cover data from European Space Agencies based on Sentinel-2 data sets, Sentinel-1 data set. Now, this is kind of readily available for 2021, and for those of you who may be keen to you could kind of look at and see how you can access them. What really matters for us is what is on the ground. So it could be like coconut plantation or patch of paddy and with some edge canopy there or some areca again and edge plantations and then paddy as well. So what really matters is that how do we really capture them? So like how I showed, when we saw that how different when you have different bands with multispectral data and creating composites, we also have different indices that one we can derive and try to capture what is the amount of greenness in the data sets. So that really also kind of helps us to kind of understand whether such plantations are healthy or not. So uh, in the sense. So if you see on the left-hand side, we have what is called as NDVA, which is Normalized Difference Vegetation Index. It's a very popular index that we often try to use it to kind of understand what is the greenness or green cover in the region and so on. And the other one is the Soil Adjusted Vegetation Index that also kind of tells you with respect to the soil and vegetation part there. Primarily, like even NDVI and things like that are used to kind of, like I said, assess the greenness. So uh, what happens is that it's basically a ratio. The value is a ratio between -1 to +1, and what we really look at it is which are positive, and the ones which are generally having a value of greater than zero point 0.2, zero point 0.3 is inferred to be more greener. So the dark greener are the ones which are supposed to be more healthier and things like that. So if you have access to a very high resolution satellite data and you're simply able to derive NDVI out of it, one can really kind of figure out, to look at whether if your patch needs water or things like that, or how green it is, and or things like that. So there are a bunch of things that are possible. Well, I'll just quickly shift gears to look at streams, as in some things that is also of interest to some of us. And what we really also try to do is try to see how we can uh, capture what is happening with respect to watersheds and water bodies and at large, and then larger riverscapes itself. So these are headwater streams, which are basically first order streams that would typically origin at like, let's say in the Western Ghats, or for Shimsha, it is Devra and Durga Hills. So it kind of flows from Devra and Durga and flows down, uh, and eventually kind of passes through, this is Gubi tank, where we have an overflow weir and then passes through that. And so eventually, this was in 2023 when we had very good rains, and uh, the river was flowing in full steam. What we have been trying to look at is the overall Chimsha River watershed itself, and what we realize or see that is that even within a watershed like upstream of Shimsha, which is a sub-basin of Kaveri, uh, there is a potential of runoff yield of about 3.5 TMC feet, which I think is pretty significant in the sense about 3.5 to 4 TMC feet is something would roughly translate to about 250 million liters per day, uh, something that Bangalore would consume about one-sixth today in that sense. So it's a very significant amount of water that, also gets drained out in these catchments. And this is something that we've been trying to look at. And uh, data for this was also like sort of derived from some of the satellite data sources, like the digital elevation models that are used. And then there are special methods to kind of derive stream orders and then also estimate what is the uh, yield from that. And then we also have recently did some work in the Goat Basin in Maharashtra, where we're trying to look at what is the impact of water quality on different land cover classes. So you kind of move over the stream of upstream of Goat to kind of downstream and see what is happening across different landscape characteristics. This is kind of gives you a sense of, how not only on remote sensing, but also how some of the regional or local activities would be influencing what is happening with respect to the water quality. Now, on the one hand, we know what is the land cover, but on the other hand, we are also measuring water quality and then trying to see what is the effect of this, as in how land cover is influencing water quality and things like that. And what we clearly see is that upstream data points that you see on the left-hand side primarily indicate better or uh, good water quality there. And as you go down towards the some of the urban areas and downstream, they're clearly polluted. And one clear reason is that also because you also have a bunch of croplands and built up, which is like that is significantly causing all of this. So we're kind of it also helps you build a macro perspective, or if not a very smaller thing, or but at least some regional perspective to look at what's really happening. So moving on, I think something that we're also trying to work with the state resource department also to at Advanced Center for Integrated Water Resource Management is to see uh, build applications on estimating yield and delineate catchments on the fly. So if you click on any point across, so we are able to kind of derive what is the potential catchment. And based on, so the good part is since KWRIS, Karnataka Water Resource Information System, also abbreviated as KWRIS, has data that is kind of has all the rainfall data that is kind of captured from IMD and Karnataka Water Resource Department. We can create a filter like looking at last 10 years, 20, 30, 20 years or 30 years. And based on those decadal averages, we can derive what is the yield for such a region and things like that. So we've been able to kind of, work through this, and this has been a very interesting experience for us as well. Then the one of the other such things applications that we helped build was also to look at what is the surface mapping across, and JRC is a global surface water mapping data sets that is available, and kind of customized it for Karnataka to kind of look at what has happened. And because over different decades, right, from 1984 to 2021, we have like data that you can look at and derive different set of things based on for water resource applications and so on. The next one is actually very interesting is because one of the other data sets that I mentioned, apart from optical remote sensing, is the synthetic aperture radar data, which is the SAR that we get also from Sentinel. uh, One imagery is kind of that helps us to kind of it's very useful because Sentinel is radar imagery, so it doesn't really rather the clouds doesn't really affect them. But they're also very good in capturing reflectance based on water. So if there is any water inundation and things like that, that is very useful. In fact, one of the other work that we have done for the Central Water Commission is also to look at sedimentation in about 31 reservoirs across the country using synthetic aperture radar data sets itself, and kind of trying to assess that. And similarly, what this is done is that we kind of extended this to kind of look at how this can be really looked at for if there is any flood event and what is the potential flood inundation and stuff like that. This is the example I was trying to share about understanding the sedimentation in reservoirs. This is Hemavati Reservoir, and we could kind of look at like water bodies becomes really dark and like, and then based on these, reflectance one, we can really look at which what is water and what is non-water, and then derive the corresponding area accordingly and establish. Yeah, I think that I will stop here. Be happy to take questions.
Okay. Thank you, sir. Any questions? You can unmute and ask the questions if any. Okay. Sir, I think Bhuvan one website is there, I
Yes,
think, sir. There we can get some of the data,
yes. Bhuvan,
geographical.
yeah, Bhuvan is there, Bhunidhi is there. They also gave India Varis is there. India WRIS. So
Mhm.
if you get for India WRIS, it also gives a bunch of data on water resources and things related. Bhuvan and Bhunidhi is also there. Just that both of them you have to register and create a login and get that. The other thing is, I think uh, at the moment, Survey of India is also allowing people to access the topo sheet. I didn't talk about the topo sheet the Survey of India produced. Uh, it's a fantastic spatial information map, what we call as the topo sheet. And Survey of India is possibly the oldest scientific institution in the country, which is over 250 years old. That was established, of course, by the British, but the good part is they ended up serving every inch of the country. In fact, their tagline is "We know every inch of the country." In the sense, people have really uh, uh, they have given lives, made sacrifices to, as in Indians have made sacrifices during the survey that happened during the Great Trigonometric Survey. And as it stands, it's one of the most accurate geospatial data that is available. Of course, satellite data is there, but I guess some of us from the old school will still like the topo sheet because topo sheet is like the gold standard of geospatial data.
Okay. Is there any scope for the students to do some projects or anything related to this, internships like that?
I think that's possible in the sense there are a bunch of things that are possible, particularly with satellite data and all of it. Uh, like I think in the first or second slide, I was also mentioning that today with Earth observation data moving on to the cloud and the leveraging of AI and machine learning models on online with cloud computation and all, what really is lacking is availability of training data. So uh, as interns, it will greatly help if some of them can help in building training data and then be like, take part in looking at things like that. That is one. Two, if some of you are already into remote sensing and working through it, there is another very exciting effort that is going on, which is called the India Open Land Cover Initiative, IOLN, under the India Open Land Cover Network. Uh, what is being done is there are groups who are working voluntarily to use Landsat data and create open land cover maps for India. And there are teams working on it, and that's something really fascinating. It will be very good to kind of really uh, anybody can join. So if any of you are keen to volunteer, you can also volunteer there.
Thank you, sir. Any questions? I think no question. If any questions, you can type in chat box so that we can read it out.
In fact, I didn't see the chat earlier. I think I had asked the question of the cloud-free images of the blue marble, and two of them had responded correctly. Yeah, it's never possible because they are all stitched as in mosaic, as we call it technically, that you filter out all the cloud-free images. So if you see, there are things that are possible. Like if you can, it's like you understand the data and then you apply some of the rules and logic to it. You can literally play around with that. So that's the beauty of it. And something that, like I said, because of the way cloud computation and all of it is happening, what I would really urge you is that on the one hand, understanding the basics or the physics or rather the science of remote sensing is very critical. Alongside, what is also very critical is I would strongly encourage any of you to kind of acquire any any more skills that you have. As in, don't restrict yourself to just looking at some of them. There are a bunch of analytical tools, programming tools, statistical analytical analysis, and all of that. So. Uh, if you're able to learn something like R or Python and apply some of the statistical approaches, that will be really amazing. In fact, some of the like larger set of geospatial data processing now, or in the previous era, it used to happen using image processing applications like Idrisi or things like that. Now things have moved way beyond, and with availability of something like Google Earth Engine or Python and R statistical package, you're likely we are ending up writing codes to run or do these analysis. So, but what is helping us write these codes or do the analysis is an sort of a good grounding on remote sensing. So one, there is no escape in understanding or getting the basics right. But two, it is also imperative that you build on the skills to learn coding and work with it. And particularly if you're able to work with R statistical package or Python and all of it, I think it can really help. And don't necessarily restrict to remote sensing, but if you know R and statistics, you can play around pretty much with any data that is thrown at you. So yeah, I would rather strongly encourage you to build or acquire more skills, so that such analytical skills that will really help you to work with any of the data sets that come by you.
How AI is impacting, sir?
AI is impacting in many ways, in the sense, so the good and bad, in the sense, the good part is like even for some of us, if there is a complex code that is written. In the past, one would really had to kind of go line by line to debug and figure out where the mistake has happened. Now, some of the AI tools can really quickly find out where the issue is. Like if it could be a syntax error, like I had missed a uh, apostrophe or a semicolon or something, and that could have simply created a bug in the program or things like that. Or if the logic uh, or applying the logic as if there is an issue and all things like that. So some of the AI tools are really helpful in fastening that, as in quickly identifying that and helping that. So it has become very efficient, if I may say. So that there is no. I think we'll have to make, like, again, if you really know what you need to do with AI, I think it'll really help. I'm not saying AI is bad there, because AI can really help if you really use it well. So things like this have been really useful. As in, from my personal experience, indeed, like I said, debugging some of the program or codes and all has been really helpful. So there is no denial on that. So those things have really helped. So the thing is, like, I think, but what really helps is there's no escape on knowing the basics, and you should be very sure as to what you're asking, because end of the day, most of these AI are LLMs, which are large language models, and these models are built on some finite set of data sets, so they can't go beyond that. So uh, it's not as uh, encompassing as a human mind in a sense. So you will have to use it as your very efficient executive assistant.
True, sir.
Dr. Sudhira, I have one
Yeah.
question.
Yes.
Is it possible to identify the different type of canopy of plants which is available using remote sensing, like this Nilgiris and other acacia and these kind of plantations? Is it possible to identify the patch and come to know that this patch of the area through the satellites comprises of this particular trees like that?
To some extent, it is possible. Like if there are Nilgiri and Acacia plantations, I think that should be possible to distinguish. In fact, that is one of the things that the subgroup working in the Open Land Cover Network initiative is trying that. So we are building samples to identify just that plantations, different plantations, and also distinguish between, let's say, moist deciduous, semi-evergreen, and evergreen forest patches also. So the
Okay,
good
sir.
part is, like, because satellite data has been available for a very long time, and things like NDVI and all of it are really responsive. So in that sense, playing around with different bands and the indices and all of it, it is kind of possible to kind of derive them.
Okay, sir. Okay, sir. Thank you, sir.
Any more questions? Okay. Sir, mm, okay. Harshini is here. While starting the session, she had a network issue. So she briefing about you and she concluding the session. So I invite Arshini to brief about Sudhir sir. Harshini, are you there?
Mom.
Yeah, you can go ahead.
Good evening, everyone. On behalf of a sincere vote of thanks is presented to conclude this wonderful session of the 27th Creative Weekend Talk. I'm Harshini, 10th Standard Vidyanidhi Public School, Gauri Bignur. It's a great privilege and honor to have this distinguished speaker, Dr. H.S. Sudhira. Dr. Sudhira has completed his PhD at the Indian Institute of Science, Bengaluru, where his research focused on urban sprawl and spatial planning for Bangalore. His work mainly explores land use and land cover changes, environmental sustainability, and the relationship between human activities and natural resources using interdisciplinary approaches. He holds a bachelor degree in environmental engineering and a master degree in geoinformation science and Earth observation. Driven by a passion of independent research, he founded Gubbi Labs, a research collective dedicated to building sustainable ecosystems and livable settlements. He also actively volunteers with the India Literary Project, contributing to improving the quality of education in government schools. Today, we are grateful to learn from his vast knowledge and experience. Thank you, sir, for your great time with us.
Thank you,
Thank you.
Harshini. She
Thank you, sir.
was in Makkala Kalika Shivra, sir.
Okay, nice.
Okay. Sir, thank you very much.
Thank
It
you.
was
Thank you.
a very informative session for us. Thank you. Thank you, one and all,
Yes.
for